So one of the reasons that we've been doing all this stuff with our algebraic numbers and the variables and things is so that we can understand how to work with this next type of number. Let's do a little quick review of our place values. So remember, this is the ones place. Can be thought of as 10 to the 0. What's 10 to the 0? 1. Anything to the power of 0 is 1. So the tens place can be thought of as 10 to the 1. The hundreds place is 10 squared, or 10 to the second. 10 to the third is 1,000. 10 to the fourth is 10,000. 10 to the fifth, 100,000. 10 to the sixth, 1,000,000, and so on. Going the other way, this can be thought of as 10 to the negative 1. Remember, a negative power is a reciprocal. So 10 to the negative 1 is 1 over 10. 10 to the negative 2 is 1 over 10 squared, or 1 over 100, 1/100th. Then 10 to the negative 3, 10 to the negative 4, and so on. Well, a lot of times, let's say we have something like 7,200,000. We often abbreviate that by saying something like 7.2 million. But another way we could say that, instead of writing out the word million, we could write it out as 7.2 instead of million times 10 to the 6th. That is our scientific notation. So let's have something like 0.00091. Now again, in scientific notation, we name the first digit, and then only one digit is in front of our decimal point. So here, this is going to be 9.1. And then we name the place value of that digit that's in front of the decimal. What place value is the decimal in, with the 9 in? 10 to the negative 4th. So it's 9.1 times 10 to the negative 4th. Now, we don't want to have to write out our place values every time we convert a number into scientific notation. So let's look for a shortcut. Our 7.2 million. The decimal point, of course, started out here, but we wanted it after the 7. We wanted it to be here. It moved 1, 2, 3, 4, 5, 6 places, hence 10 to the 6th. On our 0.00091, the decimal point started out here, and we wanted it after the 9. It moved 1, 2, 3, 4, hence the negative 4. Now, how do we know whether the power of 10 should be positive or negative? Well, big numbers are in the positive powered place values, and the little numbers, when numbers less than 1 or decimal numbers, are in the negative powered place values. So if I have that, first of all, is that power of 10 going to be positive or negative? Negative, because it's in the decimals. It's in the negative powered place values. And of course, we're going to make it 8.4, there's only one non-zero digit in front of the decimal point, times 10 to the negative. How many places does the decimal point have to move? 1, 2, 3. So 10 to the negative 3. $270 million now will become 2.7 positive or negative power. Positive, and yeah, 3, 6, 7, 8. 10 to the positive 8. Simple enough, right? Well, how about going the other direction? How about taking a scientific notation and turning it back into a decimal number? Well, first of all, that's a positive power, which means that this is a big number, right? How many places do I have to move the decimal point? 5. So 1, 2, have to add zeros, 3, 4, 5. That's 470,000. Or, of course, that's 10 to the negative 3. The negative means it's a small number. We have to move the decimal point 3 places to make it smaller. So 1, 2, add a 0, 3.0028. So in your notes, turn these two into scientific notation. And these two into standard notation or decimal notation. So this one becomes 5.6 times 10 to the 7th. 7.3 times 10 to the negative 6th. This becomes, okay, 0.000045, and this becomes 38,000. Very good. How many had all four of those right? Anybody not sure how to do them? Okay, well then, let's talk about operations with scientific notation. We've seen that when we add numbers, we must have what? The same name. With units, it must be the same unit that we're adding. If it's or with measurements, it must be the same unit. If it's fractions, it must be common denominator. Variables, it must be the same variable, same power. When it comes to scientific notation, and when it came to whole numbers, actually, lining up the columns, the individual place values, it had to be the same name. So when it comes to scientific notation, what part of that indicates a name or a place value? The 10 to the 8th. The power of 10. So when we're adding numbers in scientific notation, we must have the same power of 10. So we have 7.2 times 10 to the 8th plus 2.3 times 10 to the 8th. They have the same name, so we can combine it. Now you might be looking at that saying, well, there's parentheses, which means we should do the parentheses first. But we've had parentheses before when we're dealing with negatives and things like that, that they weren't telling us to do anything. They were just isolating that number, so we knew that that was a number, not subtraction or whatever. Same thing here. This is just telling us that this is one whole number, not different pieces to be combined. So when we add, we combine counts. What is 7.2 plus 2.3? 9.5. And then we keep the same name. So 10 to the 8th plus 10 to the 8th is 10 to the 8th. Keep the same name. So 4.2 times 10 to the negative 4.2 times 10 to the negative 13th plus 3.7 times 10 to the negative 13th is going to become 7.9 times 10 to the negative 13th. Very good. Now, it doesn't stay that simple all the time. 5.6 times 10 to the 11th plus 7.1 times 10 to the 11th. If we go to add, we're going to get 5.6 plus 7.1 is 12.7 times 10 to the 11th. We keep the same name. But we're not done here because right now we have 2 digits in front of the decimal point. So we have to move it over. Make 1.27. Now, did the number get bigger or smaller? It got smaller. It went from 12 down to 1, right? The number gets smaller, the power has to get bigger. So 11 plus 1 is 12. So, in your notes, try that addition, see what you come up with. Hit here then.
1.36. We'll get there eventually.
You add them up, you get 13.6 times 10 to the negative 9th. You move the decimal to make it 1.36. The number got bigger, the power has to, or the number got smaller, the power has to get bigger. The number gets smaller, the power gets bigger. So negative 9 plus 1 is negative 8. So 1.36 times 10 to the negative 8. So be careful with the negatives. I actually always write it out as plus 1, so it's easier for me to do. If I just think about increasing or decreasing the power, it screws me up. But if I actually write the +1 there, it helps. Now, what if we don't have the same power of 10? What if we have something like this? 4.27 times 10 to the 8 plus 9.4 times 10 to the 7th. Well, just like any other form of number, like fractions or whatever, we can sometimes change the name so that we can still add them. Usually I change them to the higher power. So this stays 10 to the 8th. Drew, put the phone away or I'm going to have to hold on to it for you. This will be 10 to the 8th. She wasn't part of your notes. The power got larger here. It went from 7 up to 8. So the number has to get smaller. Power got larger by 1, so the number gets smaller by 1 decimal place. So it's 0.94, just 0.94. So now we go ahead and add. 4.27 plus 0.94 is 5.21 times 10 to the 8th. Not so bad? So 6.4 times 10 to the 15th minus 4.2 times 10 to the 15th. Hey, Drew. So we're going to subtract. 6.4 minus 4.2 is 2.2 times 10 to the 15th. How about this one? What do we get? 0.84 times 10 to the negative 11th. Of course, there's a problem with that one. What's wrong with it? There's nothing but a 0 in front of the decimal point, so we got to move it the other way. 8.4. Did the number get bigger or smaller? This time the number got bigger, so the power has to get smaller. So negative 11 minus 1 is negative 12. In your notes, try this one. See what you come up with. So we subtract here. Our first subtraction is 7.43 minus 6.81, which is 0.62 times 10 to the 8th. What do we have to do that? So 6.2, the number got bigger, so the power gets smaller, so 10 to the 7th. How many had that? Good deal. So when we multiply, do we need the same name?
No.
So 4.3 times 10 to the 8th times, guys, 4.3 times 10 to the 8th times 2.1 times 10 to the 11th. We don't have the same power of 10, but it does not matter when we multiply. So now we multiply the counts. 4.3 times 2.1, which is 9.03. But we also multiply the names. This is why we did all that with variables and powers of 10. What's 10.8 times 10 to the 11th? 19th. When we multiply, we add the powers. Now, of course, it doesn't stay that simple. 5.4 times 10 to the negative 3rd times 7.8 times 10 to the 11th. First, we're going to multiply 5.4 times 7.8, which is 42.12 times 10 to the negative 3 times 10 to the 11th is 10 to the 8th. Good. Negative 3 plus 11 is 8. But we do have to move the decimal point to make this 4.212 times. The number got smaller, the power gets bigger, so 10 to the 9th. Very good. So try this one in your notes. See what you come up with. So we start out 8.3 times 5.1, which is 42 point what? 0.33 times 10 to the 5th times 10 to the negative 13th is 10 to the negative 8. Then what? 4.233 times 10 to the negative 7. This got smaller, so the power has to get bigger. Negative 8 plus 1 is negative 7. How is about what's that? Well, this divided. So 2.72 divided by 1.6 is 1.7. Then we also divide the names. 10 to the 8th divided by 10 to the 5th. 10 to the 3rd. The tough part is when we bring in negative powers like this. 3.42 times 10 to the negative 6 divided by 1.8 times 10 to the negative 13. So 3.42 divided by 1.8 is just, not everybody at once, 1.9. Well, this is negative 6 minus negative 13, which becomes negative 6 plus 13, or positive 7. That's why I said, with the negative powers, when you're dividing, it can be tricky.
How is that? How do you go from something so small to multiplying another thing so small that it just gets...
It's not multiplying, it's dividing. You're dividing by something so small. So what you're saying is, how many times can you take this out of that? That's just like, you have 1/4, which is something kind of small, right? But if you divide it by 1/8, there's 2 1/8 and 1/4. You get something big. How about rule 4.62 times 10 to the 7th divided by 2.1 times 10 to the negative 11th. So 4.62 divided by 2.1. 2.2 times 10 to the 18th. Very good. So then, how about we go 2.4 times 10 to the 4th divided by 5.04 times 10 to the 9th. What do we get? Niner? We get 0. What? 476 times 10 to the 4 minus 9 is negative 5. But just like with our subtraction, we have to move that over. This becomes 4.76. Now the number got bigger, so the power gets smaller. Negative 5 minus 1 is negative 6. Because it's 4 minus 9 makes the negative 5. Up here, 7 minus negative 11 becomes 7 plus a positive 11, which is 18. Those negatives are kind of a pain, I know. How about this? 1.2 times 10 to the 5th to the 3rd power.
Okay.
Well, what's 1.2 to the third power?
Um,
1.728.
okay, thank you.
What's 10 to the fifth to the third power?
10 to the 15.
10 to the 15th. You're just multiplying the powers when you do the power of a power. So this one, 2.1 times 10 to the negative 7th squared. What's 2.1 squared? 4.41. 10 to the negative 7th squared? Negative 14.
Wait, I thought a negative times a negative was positive.
That's negative 7 times 2, though. When you're taking a power of a power, saying it's negative 7 plus negative 7, if you think of it that way. 4.5 times 10 to the 13th squared. What's 4.5 squared? 20.25. 10 to the 13th squared is 10 to the 26. We multiply by 2. Now we're not done on this one. What do we have to do? 2.025 times 10 to the 27th. Very good. How about this one? What's 5.1 to the fourth power? 676 point what? We'll just go 676.5 times 10 to the 20th. Now, of course, we have to move the decimal point. This will be 6.765. Now, the number got smaller by 2 places, so the power gets larger by 2. So 10 to the 27th. Make sense? No? You okay with it? Sort of? You sure? Well, if we went 1 spot, this would have to get bigger by 1. When we went 2 spots, that's going to get bigger by 2. Right. The squaring, you're just squaring the number and then multiplying the powers. Okay. Okay. Well, if the number gets smaller, the power has to get bigger. So this went from 676 down to 6. So it got smaller by 2 decimal places. So the power gets larger. Think of it this way. What we're doing is this. We're breaking this 676.5 is 6.765 times 100, right? Or 10 squared. So you're adding that 2 to the power. So the square root of 4.41 times 10 to the 18th. What's the square root of 4.41? 2.1. Times 10 to the 9th. You divide it by 2, just like we do other variables in our powers. How's about the third root? 1.728 times 10 to the 15th. What's the third root of 1.728? 1.2 times 10 to the 5th. You divide by the 3 for the powers. Any questions? Too many to ask? Now, there is a variation of scientific notation referred to as engineering notation. Engineering notation is different from scientific notation in 2 ways. One, scientific notation restricts you to exactly 1 digit in front of the decimal point. Engineering notation, you can have 1 to 3, 1, 2, or 3. However, engineering notation, you can have any power on the 10. In engineering notation, that power must be divisible by 3. So 10 to the 3rd, 10 to the 6th, 9th, 12th, whatever, negative 3, negative 6, negative 9. So if I have 580 million, and I want to put it into engineering notation, Can I move my decimal point 3 spots?
Yeah.
Sure. 1, 2, 3. Can I go 3 more?
Yeah.
Yeah. 4, 5, 6. Can I go 3 more? No, I cannot. It's okay to have up to 3 digits in front of the decimal point in engineering notation. So this one here, no, it's not. 1, 2, 3. Can I go 3 more?
No.
Yeah, 1, 2, 3. That's 72 times 10 to the negative 6.
Wait a minute.
You have to have between 1 and 3 digits in front of the decimal point. There wasn't.
Okay. Let's see where I'm missing.
Here's the one that's actually trickier. I move my decimal point, 1, 2, 3. Can I move 3 more?
You add another zero.
I have to, don't I? Because right now there's nothing in front of the decimal point. I have to add that 0 and go 1, 2, 4, 5, 6. So that's 570 times 10 to the negative 6. So that's a little trickier. So why is it that we would ever have this? Scientific notation is bad enough. Why would we have this variation of it? Well, because the metric system, we've got our meters. We're gonna skip deci and centimeters and go straight to millimeters. Then we'll skip down to micrometers and nanometers and whatever. We'll still just stop there. Going the other way, we're gonna skip deca and hecto and go to kilometers and go up to megameters. But more importantly, more often than not, it's stuff like this, like volts. You have millivolts and microvolts, kilovolts, megavolts, or amps. You have milliamps or microamps and kiloamps and so on. And in the electronics field, and even in figuring out electricity in a house, if you're going to do a basic circuit in your house, the rule is the voltage is equal to the current times the resistance. So if you know the voltage that you're being applied, either 110 or 220, why is current I?
Why is current I?
I have no idea. Because A was already used for so many other abbreviations that they had to go with I. A is used for acceleration, and there's a couple other things it's used for. But anyway, let's say that we have our current is 24 microamps, and our resistance is 1.2 kiloohms. Well, when we go to do this, we can think of the main unit as being 10 to the 0. Milli is being 10 to the negative 3. Micro is 10 to the negative 6. Killi, 1,000 is 10 to the 3rd. Mega, 1,000,000 is 10 to the 6th. You can see the powers of the 10 are all divisible by 3. So metric prefixes are really nothing more than engineering notation. So when we're looking at this here, the current goes in as 2.4 microamps times resistance of 1.2 kiloohms. We can rewrite that. Micro 2.4 can become 10 to the negative 6 amps. Kilo 1.2 times kilo is going to be 10 to the 3rd ohms. Now you said they're different names, but if we were adding or subtracting, that would be bad. But when we're multiplying, we can multiply things with different names. So 2.4 times 1.2 is 2.88. 10 to the 6th times 10 to the 3rd is 10 to the negative 6 times 10 to the 3rd is 10 to the negative 3rd, right? An amp times an ohm is actually a volt. I don't expect you to know that right now, but it is. So what is 10 to the negative 3rd is what prefix? Milli. So this is 2.88 millivolts. So when you're working with electricity and other quantities, if you know your engineering notation, it allows you to do the operations with the metric prefixes. Make sense? No? In the big book, on page 205, it is exercise 6-12A and exercise 6-12B. Do the odds there. On page 208, exercise 6-12C. Page 281, exercise 9-17A. Page 282, exercise 9-17B. And on page 283, exercise 9-17C. Do the odds again, double check them.